Hi, my name is Sarah Masaga, and I'm presenting our abstract concerning cortical bone adaptation in response to daily exercise. Exercise increases strain in bone and has been shown to result in bone adaptation, either through changes in shape, mineral density, or both. Exercise during youth, when bone is already rapidly growing and adapting, may allow for directed bone remodeling. In this study, we evaluated the effects of two different exercise interventions, flat and incline treadmill exercise, on cortical bone adaptation of the femur in juvenile sheep. After 60 days of exercise, the sheep were sacrificed and the right femur removed and scanned with micro-CT. 10 slices of interest were identified in the diaphysis, and those regions were further divided into anatomical quadrants for analysis. All image processing steps were performed automatically using custom MATLAB code to prevent user bias during segmentation. In all subsequent figures, control sheep will be green, flat exercise will be orange, and incline exercise will be blue. Location in the diaphysis is given on the y-axis, with 0 being the most proximal location and 90 the most distal. Each column represents a specific quadrant. Broadly speaking, exercise resulted in more dense cortical bone than control sheep, and trends are quadrant specific. To simplify the data, we calculated the percent difference between each exercise group and the control group. When looking at all locations in the diaphysis, the anterior quadrant had the greatest percent increase in density between exercise and control sheep. Flat exercise resulted in slightly greater increase in cortical density than incline exercise when pooling all quadrants and locations. If we look at cortical bone area fraction, we can see that flat and incline exercise elicit similar increases in area fraction when compared to the control sheep. When looking at percent differences, the posterior quadrant experienced the greatest increase in bone area fraction for exercise sheep, followed by the lateral quadrant. When looking at all quadrants together, the largest increases in bone area fraction for exercise sheep tend to occur in the distal portions of the femur. This trend is evident if you directly compare the percent difference at location 20 in the proximal region and location 70 in the distal region. We normalized our cortical thickness measurement by dividing thickness at each degree by the radius. Realizing that we would lose information by only looking at thickness per quadrant, we broke the cross-section into 8 subsections. Median normalized thickness per subsection was calculated for each subject at each location in the diaphysis. Then, we calculated the median normalized thickness per subsection for each group and calculated percent differences between each exercise group and the control group. The median normalized thickness per subsection and group was tested for normality using a Shapiro test. A significant difference was tested using KS test. Significant differences from the control group are marked with an asterisk. When comparing these percent differences, we found that the flat exercise group resulted in greater percent increase in thickness than the incline exercise group and had more statistically significant differences. The lateral anterior and posterior medial subsections had the greatest increase in thickness compared to controls. The posterior lateral, followed by the lateral posterior subsections, had the next greatest increases in cortical thickness for exercise sheep. Overall, daily exercise in growing sheep resulted in spatially specific cortical bone adaptation. However, the increases in density and thickness due to exercise occurred in different locations. Although exercise at an incline results in increased step frequency, smaller knee range of motion, and different muscle activation patterns than flat exercise, we did not see many significant differences in structure and composition between the incline exercise and control groups. In the course of analyzing CT scans, we noticed that the distal third of the bone tends to have more cortical pores, and that these are concentrated in the lateral and posterior quadrants, the same locations where the greatest changes in thickness and bone area fraction occurred. Differences in cortical pore networks between groups may help identify exercise effects on cortical bone microstructure or evidence of increased modeling, and is the next step in this ongoing project. I would like to thank my funding source and my amazing lab group, the Tissue Biomechanics Lab at UIUC. Thank you for your attention.